3D printing addresses those challenges, and then talk a little bit about the technology choices we've made in our metal 3D printing systems. Then we'll do sort of a broad swath across dozens of application examples from the manufacturing floor, and then do a deep dive on a handful of case studies right from the manufacturing floor. So let's get moving. So what are the manufacturing floor challenges? So first, if you think about as a product is being developed, as it moves from product development to manufacturing, there will be a need, of course, to set up a production line. And sometimes it could be assembly of components that are either off the shelf or custom that are being delivered. And other times it's the manufacturing, it's the fabrication, it's the stamping, tooling, molding. So there is an effort involved in the time, the cost to set up a new production line. And it might be modest for some products. For other products, automobiles, for example, it's literally billions to stand up a new production line. And so one challenge is just the time it takes and the effort and the non-recurring engineering charge to create and move to manufacturing a new product. Second, related challenge is the lead time and cost specifically of new tooling. It could be stamping, injection molding, extrusion dies. Third challenge is the maintenance, repair, and operation, sort of replacement parts for the manufacturing floor. Parts wear out, they need to be replaced. Next is a lot of those parts, or at least some of the tooling in particular, those are hard to machine materials. And so machining them in the shop is not an easy thing. And finally, just the labor associated with there's parts that need to be made. They're probably made in relatively low volume, the tools themselves. And so to machine them, so they have to be machined. They can't be cast. And so machining them takes a long time and takes away the machining capacity from other things that the machine shop on the manufacturing floor could be doing. So let me pause for a second and see which of these are actually challenges you're encountering. I'm going to ask my colleague to put up a poll, and let's see which of these challenges sound familiar. And then we'll share the results, see how your world matches that of other folks. Interesting. So we'll share this in a minute, but it looks already like a little over half the challenge. The first challenge is the lead time and cost of new tooling. And second is, yeah, the effort and time just to bring up a new manufacturing line. So here are the results. So you see the number one is lead time and cost of new tooling. Almost 6 out of 10 of you are encountering that. And then next is time, cost, and effort to bring up a production line. Okay, terrific. So we'll see how 3D printing is affecting all of these. So what can 3D printing do here? So 3D printing for the manufacturing floor, and the reason I say for is because this is around the tooling, jigs, and fixtures, as opposed to what gets 3D printed on the manufacturing floor and use parts. That's the next slide. So 3D printing on the manufacturing floor. So you can have the notion with 3D printing of nearly real-time tooling. You need a part and you can have it in a short number of days, as opposed to the lead times of either ordering it and waiting for a custom tool to be made, EDM, or even just CNC, but that could be a complex operation. The geometric complexity of the tools is free. What you get with, and we'll see these in more detail, but here's some examples of, this is end of arm tooling, and it's, you see it's lightweighted to reduce wear and tear on the robotic arm. There's relatively complex tooling available. So the geometric complexity is free. You can print, if you can imagine the 3D shape, you can probably print it. You can offload, of course, a lot of the work, you're now printing it instead of machining it. So there's machinist labor is not involved. And you don't need, if you think about a manufacturing floor, you have replacement parts. You can't have a production line go down. And so you often have a stock room with maybe 3 or 5 replacement parts times 100 or times 1,000 different parts. So instead of keeping that inventory, you could just print what you need when and where you need it. So that's the promise of 3D printing, and that is how both plastic and metal 3D printing is being used. Then, so that's printing for the manufacturing floor. And then there's, of course, 3D printing on the manufacturing floor, and that is the value proposition is mass production without tooling costs, without tooling delays, without the constraints of tooling. And so you can now print a broad range of infinite range of geometries, parts. We'll take a look at some of these, but you see you can do quite intricate parts, really on demand. Here's a part that might otherwise be cast, but there's an effort and non-recurring engineering charges associated with casting them. With 3D printing, you can just manufacture them. So both of these, the tooling, jigs, fixtures, as well as mass production, are relevant for the manufacturing floor. And now technologies are available to actually deliver on this promise. So let's take a look. Desktop Metal, we're a company founded 5 years ago, and our mission is to make 3D printing accessible, available for engineers and manufacturers. So that means during the design phase, as well as part production. We've started shipping 3 years ago with customers all over the world. You'll see some big names there, some leading automotive vendors, others, as well as smaller companies that are bringing in 3D printing because they want to be more agile. This is another view of the customers if you are looking from space. And we have 4 products. 4 main product lines. We have a composite fiber printer. So that's the innovation there is you can print continuous fiber reinforced composites. And then we have 3 metal systems, an office-friendly studio system, a shop system, so it's mid-volume production, and then a production system if you need to make tens of metric tons of parts per year. So tens of tons. I will mostly focus today on the studio system examples for the manufacturing floor, although I will touch up on how the mass production printers are relevant as well. So the approach we've taken is printing systems built around the chemistry and the powder supply chain of metal injection molding, MIM. The 3, and I'll talk a little bit about how that works, but this is this approach, MIM-like approach, using powdered metallurgy principles and metal injection molding powders is applied across all 3 of our products. We have the studio system, which is the office-friendly. So you open the door, you wheel them in, and you start printing. We're sintering right next to our desks. Then there's the shop system for when you start to get into volume production. You want to make hundreds to maybe thousands of parts every day or 2. Down to a production systems where you might be producing millions of parts or more. So a little bit about metal injection molding, just to give you a little background on it. So this is a powdered metallurgy process. So powdered metallurgy is over a century old. You know, the original, plenty of parts in the first automobiles, connecting rods, others were made with powder metallurgy principles, pressed and sintered, where you have the metal powder, you put it into a kind of 2.5D form, and you sinter that at high temperature into that shape. Metal injection molding is basically taking that approach, but it's used to create metal parts with fine detail. And so this is a technology 50 or 60 years old, widely used, and so there's now established standards for characterizing the materials, and over 100 different alloys are compatible with the process. Let's take a look at the actual process. With metal injection molding, you start with metal powder and you mix it with a polymer binder into a feedstock, these pellets. And now you have a process that is the next step, very similar to plastic injection molding, which is this mixture of feedstock is heated such that the polymer binder melts, flows into molds. The metal powder comes along for the ride. So that is how the shape is created, the part shape is created. Then there's a debind and sinter step. In the debind step, the polymer, much of it dissolves and finally in the furnace, all of the remaining binder evaporates, and the metal particles come together through solid state diffusion bonding and become the metal parts you're familiar with. We've applied that in the studio system. Again, the three parts. You got the printer, you have the debinder, and the furnace. And it works quite analogous to this MIM approach, except we create, instead of a feedstock into pellets, we create it as rods. Now the rods, it's bound metal, and so it's now safe for the office. Those rods are used in a FDM-like printer to create the shape, and then there's a debind step with a debinder and a furnace, and that's start to finish how the process works. The studio system, the big win there is it is the world's first and only office-friendly system. It's great for low volume applications. And so functional prototyping, jigs, fixtures, replacement parts is great. You don't need to, for example, machine the part off of a support like you do with other metal 3D printing approaches. And it's easy to change materials. Today, what we've shipped are 4 materials that are 17.4 pH steel, 316L stainless, H13 for tooling applications, 4140 chromoly steel. But in general, this approach, the MIM approach, is compatible with over 100 alloys. So you can expect a much broader palette opening up. And we have started shipping in almost 50 countries. What you get out are near net shape parts. And so let's see, parts that are close within, how close? Realistically, within 1%. Could be better tolerances depending on the process, but you get parts that are like fine castings, those kinds of tolerances. The critical dimensions, if you need to hold a tenth, then you need to do post-processing like CNC or EDM or grinding. So you save most of the effort, or sometimes all the effort if you don't need to, the submicron or micron level precision. And what you get back are the alloys, and you can machine them, CNC, EDM, etc. The ideal part size is, the sweet spot is parts that fit in the palm of your hand. And so that might be a 5-inch cube or softball-like sizes. The build volume is more, it's like a loaf of bread, 12 by 8 by 8, so you can print a bunch of parts. We can make larger parts, but though that's kind of the sweet spot. And of course, afterwards, you can do everything you do to metal parts, whether it's welding, heat treatment, etc. The big business impact, the big benefit, there's 3. There is optimizing the part performance. So what you can do is you can make better parts. With 3D printing, you can consolidate assemblies. You can, by creating shapes that you can't with other manufacturing processes, you have a whole new design freedom, and that can result in better parts. So that's one benefit. The other is rapid prototyping. You get part to market faster. What I'll focus on today, though, is what is the win for manufacturing? Manufacturing, there's 2 giant opportunities. One is you can finally do mass production without the need for tooling. So that means you don't need to make molds, you don't need to make stamping dies. You can create a range of parts. You can have both mass production and mass customization. Imagine every part in a build. You're printing 16 liters worth of metal parts, or 50 liters worth of metal parts every few hours, and every part is a little bit different or a lot different. You start with a digital file, so as easy as you can change the digital file, you can print what you need. So the first win is mass production of parts without tooling. The second is being able to print all of the things you need on the manufacturing floor. So that's jigs, fixtures. It's things that hold, and as well as things that deform parts. Metal, extrusion dies, stamping, sheet metal stamping, and mold inserts. We'll see examples of all of that. So let's talk a little bit about rapid tooling for the manufacturing floor. I'll show a few examples, but you can do things like a drill alignment jig. There's a variety of end effectors we'll take a look at. Just a bunch of parts. What they all have in common, these are from a diverse, so the smartphone fixture is obviously from a consumer product, electronics component. There it needs to be metal because it's maybe rework is happening. It's a high temperature operation. Drill alignment, there might be forces involved. There's definitely, you'll see examples with the robotic end effectors, a lot of forces involved. What they all share, though, is they're relatively complex parts that are not trivial to machine. And you need just a few of them. And for that reason, you're not going to set up a whole mass production line for these to produce these manufacturing aids. You need just a few of them. And so 3D printing is a great way, because the alternative is machining, and the machining can be both expensive. You might have capacity bottlenecks. It's quite involves labor, and depending on if it's for tooling. So the next stage, tooling. The whole point of tooling is these are hard metals, and so machining hard tooling is actually quite tricky. You can go through a lot of carbide tools. So it's a big win, for example. So you see this first example of a mold insert with a conformal cooling channel. So this is the part that's actually getting molded. We printed this part just halfway. So you see there's an internal cooling channel. The big win there is you can dramatically increase the cycle time. The cooling time increases, and so you can dramatically increase the frequency with which you're molding these parts. And so tooling, being able to print tooling on demand, in fact, you can be printing tooling while the product is being developed. It's really parallel with the product being developed. You don't need a lot of lead time. And so by the time the product's ready to be manufactured, you got your tooling ready. And you can turn to a growing library of metal materials. By the way, if there's questions, feel free to put them right in the Q&A portion, and we will endeavor to answer them and try to stump my colleagues. I try it every day. All right, manufacturing tooling, jigs, and fixtures. So another whole category is things that hold. So let's take a look. Let's do a rapid walk around the world. So this is a part that places an O-ring around another part during the manufacturing process. This is the end of the robotic arm, and so it stretches, puts the O-ring on, and compresses. And so this is, I don't know if you can see, I think you can see, these are relatively fine end effectors. And so being able to machine them, you can imagine you have a ball end mill or whatever cutting tool, you're gonna, I mean, these are probably a millimeter, less than a millimeter in thickness. These would bend, these would deform during bending. And so it's a pretty extensive machining process, pretty laborious, pretty small stuff, and it's quite tricky. Now you can 3D print. You can 3D print a whole bunch of them at a time, and have them ready when you need them. Let's see. Here's another example that we'll see. End of arm tooling. So we'll see more when we get to this particular case. End of arm tooling, of course, refers not to the fact that it's being held at the end of his arm, but it's the end of the robotic arm. And so this is an example of end of arm tooling. It picks up a heavy, hot metal part being forging, I believe. And the big win with end of arm tooling is lightweighting it. The less it weighs, the faster the robotic arm can move around, the less inertial loads there are. So you can have a faster and more reliable, there's less wear and tear on the robots. You can do, of course, complex shapes. This is a drill alignment jig. We talked a little bit about the smartphone fixture. Let's spend a second on mold and tooling. So one of the materials available is H13 tool steel. So this is great for both hot and cold work applications. In another second, I'll show you guys it actually in action for at least in one place. But you see, here's the familiar stress strain curve. Well behaved. There's the S-sintered. S-sintered, the parts come out from the furnace fully annealed with no memory of the shaping process. And in fact, if you cut and take if you cut and section them, you literally cannot tell X, Y, and Z axes. The grains, the crystal structure looks identical. You get 96 to 99% dense parts, and the voids are typically 5-micron voids, evenly distributed. So it's well behaved, not unlike a very fine casting. So tool steels, and you can of course heat treat. You can heat treat all of the materials. Even the 17.4 pH steel becomes much more much harder. You can the tools 17.4 pH steel comes out from the furnace annealed 25 to 30 Rockwell C, and through the heat treatment you can get it to 45, and through plasma nitriding, a case hardening process, you can get it to 65. So a broad array of heat treatment processes are available. Let's see. I'm going to just check the comments. So it looks like there's some folks asking questions. Instead of using the chat, if you look in the Q&A, then my colleagues will be able to answer your questions. So try the Q&A. All right. So let's take a look at some examples. So there's the asthma inhaler for the mold. Here's the actual part getting molded. It's an insert. You can make cooling channels. And so the big win here is twofold. First, you print a part that's near net shape. You may still need a couple passes to get the exact surface finish and dimensions you need, but by getting the tool steel to near the net shape you need, you don't need to start with a large block of steel and go through a lot of wear and tear on your carbide tools to machine them. The second one, of course, is the ability to create a geometry that you can't produce any other way, which is an internal cooling channel. And so here's an example of that. And basically, the closer you can get the cooling channel to the part, the faster you can cool the part down and increase the cycle time. And typically that can increase things 25, 40%, which is a big deal for relatively low margin kind of operations. And then, of course, here's that mold insert getting, for the critical dimensions, you can machine them. So here it's getting machined for to fit perfectly in the mold cavity, and then here's another mold insert getting EDM finished. And do zipper molds. I think I have an example of that. I think I got an example. Where is it? Here it is. See, there's so many metal parts around. So here the idea is, first of all, a little background. What is this? So it turns out, news to me, but zippers are a fashion element. And so now imagine you need to produce maybe a run of custom zippers, one every, you just need 500 of a particular zipper for a luxury bag or something, or a piece of clothing. Instead of printing or machining whole molds, you can have just inserts. And so print an insert, and you can do that with the fine resolution printhead from the studio system and use it right in the mold. And so now you can do relatively small, precise features that might not even need post-processing of the mold insert. Do extrusion dies. Here's an example. So this is a twin screw extruder that's pushing a dense ceramic slurry, mixing and pushing a dense ceramic slurry through this extruder. I'm going to take this off. So here's the interface, and here is the part in question. You see there's a gasket on this end. So you basically start with a circular profile, and you end with a rectangle. And it's rectangle because the final part, it's like you're extruding pasta, except you're extruding ceramic mixture. What you need, what the goal here is to create a rectangular shape. You need to start from circle because that's the interface, that's the standard interface to the extruder. It's an easy part to model. This is a loft. If you have a parametric feature-based solid modeler, you start from the circle, you draw the profile, you wind up with a rectangle. But it is not an easy part to actually reduce to practice, to create. You need a 5-axis machine, and we've looked at a number of bids. Our customer looked at a number of bids, and it would be $2,000-$3,000 to make this shape. So this is, you could see this is probably 6 inches or so, maybe 7. So With the studio system, it's an order of magnitude less. It's $60 or $80, and you have the part. You can make complex extrusion dies that are either complex shapes or they're either difficult or impossible to create. So this one you might EDM this shape. Here's an extrusion die with a familiar 80-20 profile. In this photo, you might see that this surface is particularly reflective. You can do, of course, extrusion honing so that whether it's aluminum or zinc that flows through here or plastic, it flows easier. So the same things you might do to dies, you can do to these dies. Sheet metal tooling. So it's not, of course, it's not, 3D printing is not a win in every single application. So you got to look at what is a sufficiently complex part, what is hard to machine, or where do I not have the lead time to wait. And so for some parts, even sheet metal tooling makes sense to print. So you can do embossing tools. We've seen stamping, bending, countersinking tools. Here's a couple of these parts. So this is part of I believe this is a embossing, so that for legs on a piece of flat sheet metal forming. You basically go from art to part. Here it is in SolidWorks, and there it is, those very parts printed a couple days later. So sheet metal tooling, bending, I have examples somewhere here, but you get it. Here's a fun little example, a blacksmith touch mark. So H13 tool steel. Here are the inserts printed with a custom stamp of this blacksmith. And you know what? I'm going to turn down the audio so you don't hear I was told this is whoops, that's not it. I'm going to play this. So you're going to see, so this is a couple thousand degrees Fahrenheit part getting this stamp from the blacksmith using this H13 printed insert. So let's see what that looks like. Really, we're showing you the video so you get a sense for, okay, these parts are pretty tough, pretty hard. You can do hot work with them as well as cold work. So now let's take a look at the actual stamp. And there's his little, I don't know if that's an S or a Z. And all right. And here is, again, the touch mark. Here's the resulting stamp. Works great. All right. So now let's take a look at some case studies. So the first example is Alpha Precision Group. Alpha Precision Group is in St. Mary's, Pennsylvania. It's a leading vendor of precision metal components using, for the most part, powdered metal and the metal injection molding approach. They wanted to do two things. One is reduce the tooling costs for their mass production lines, and the second is being able to engage their customers earlier during the design process, and so being able to produce parts in low volume as samples to actually win business. So let's see. So there's a number of examples. They've literally printed hundreds of parts with their studio system, hundreds of tooling, jigs and fixtures kind of application. I'll show you just a couple. This is that light-weighted end-of-arm tooling example. So this comes together. It's got to be metal because it's holding a heavy metal hot part, and it manipulates it and reducing the end-of-arm tooling by, you see there's light weighting going on. This would not be trivial to machine. This is a lot of different setups. You see some of the radii are relatively small, so you'd need probably a small ball end mill to hog out a lot of this material. With the 3D printing, that geometry is free. Another great example, let's see if I have that. I do. The chuck jaws to hold work pieces together. So this is holding parts during a machining operation. It's a large part. These jaws come together and grab the part. I'm going to hold it up. You see, this is not a trivial part to machine. You could machine it, but this would be a lot of different setups, and the three would easily keep a machinist busy all day. Now you can just 3D print this part and throw it on the manufacturing floor. Another example, I love this one, and I'll tell you in a minute why. So this is an assembly line screwdriver. This originally was a manual operation that somebody would screw in components on the production line. That it's obviously a repetitive task, and you can imagine repetitive use injury, probably also not super fun to literally just do that all day. And so the manufacturing engineers came up with a pneumatic tool to replace that screwdriver. Instead of a human, now there's this nice ratchet set that works great. It's a pretty complex design. I'm going to try to take this out without having the 20 parts fall apart. So you see, this is a ratchet set, and this is the unit that is at the heart of this device. Why do I love this example? This is an example of a small company walking around the manufacturing floor, seeing an opportunity and designing something for 3D printing that they would never have somebody machine it. Because if somebody was to machine this would be a $10,000, if at all possible, job that they would send outside and probably get back in something like 2 months. Instead, they conceived the idea and within a week had this part. And so this is a dramatic both lead time savings, so it's days instead of a couple months, and dramatic cost savings. It's $700 instead of over 10,000. So by the way, I see questions coming in. Keep asking, and we'll keep answering. There's more examples from their manufacturing floor. We only have limited time here, so I'm not going to show you. There are hundreds of parts, but there's a coining fixture. There's a thread checker. This pushes a part into essentially a way to check whether the thread on a molded part turned out fine. This part wears, and so the ability to replace it once in a while, to print it and easily replace it on demand is an important one. And the big win for Alpha Precision Group is a dramatically compressed time and cost of manufacturing tooling. And they're not just doing things cheaper and faster, they're doing things they wouldn't have otherwise. And so that is a very, very cool thing for a small manufacturer. The other big win is the elimination of all the labor-intensive manufacturing steps by designing new tooling. And finally, they can produce on-demand parts both during the early stage of their sales cycle as well as aftermarket, so that they don't need to maintain a tool. You know, imagine you do a production run of 5,000 parts, then you keep the tooling around because 3 years from now or 5 years from now, by contract, you're obligated to, if there's a requirement for some replacement parts. You might run a tool a day or two to produce 20 or 50 or 100 parts years after your mass production run. But in order to do that, you keep tools around. Instead, you can just print the actual parts on demand. And so that's the other use that APG is doing. Another example from the manufacturing floor is Egger Tool and Die. It's a 40-year-old company in Ontario, Canada. So they have quite a broad scope for additive manufacturing. They make largely automotive stamping. Their manufacturing line is automotive stamping for automotive parts and welding of some of those parts. The things they 3D print are anything for the manufacturing floor if it meets 2 of 3 requirements. 2 of 3. So either the part is cheaper and or it's faster to 3D print, and in particular for the end of arm tooling, they can reduce the weight. So if they can reduce 2 of these 3, they apply 3D printing, and they've seen a lot of benefit to that. I'll show you just a couple examples. Again, because we don't have time for any one of these beyond just a few minutes. So end of arm tooling, started out on the manufacturing line with nylon printed parts with steel inserts, and by redesigning them, they're actually as single pieces made of steel. They're both lighter, stronger, and cheaper. And so that's a win. They've used Studio System for stamping dies. In fact, welding. So stamping dies with H13 tool steel, and in fact, welding some of the materials together. The parts weld beautifully. There was another application where there's a servo-driven timing belt pulley. So this is a pulley that helps. There's a belt, and then there's the servo moves it around, accelerates it, reverses direction. If they can reduce the weight of the pulley, and by the way, make it cheaper, then they can move the pulley a lot faster, A, and B, there's less wear and tear on the machine. So they came up with a design that is now both lighter and it's a single part instead of machining and assembling a part together. And here's that part, that belt pulley printed. And they're also starting to do some experimentation with, as we bring other products like copper to the market, they're printing copper electrodes for welding with the internal cooling channels. That's a cool example. So business impact is you can lightweight end-of-arm tooling, you can print tooling components for stamping dies, and starting to experiment with new materials. Next example I'll show is a sheet metal fabricator in Italy. This is founded in 1969, so company is as old as I am. So they've been around in a variety of markets, both residential and industrial, and they make a variety of sheet metal cabinets. So the challenge there is replacement parts for the manufacturing floor. Replacement parts for the manufacturing floor. So there's basically for these MRO, maintenance, repair, and operation parts, there's a delay in there's obviously a lead time when you're ordering a part that you don't have. The part may need to be machined wherever you're ordering it from, and then for the parts that move fast, whether it's end-of-arm tooling or other applications, you want to reduce part mass. And for all these reasons, so here's a part that there's 4 clamps here. This is a punching machine. So you see there's 4 of these clamps, and the clamps handle the sheet metal and move it from one step to another. And it's typically cut with a 2 or more week lead time, machined right from a block of steel. So this is a pretty large part. You see 200 millimeters. So this is over 8 inches long. It's a relatively large part. So they printed it with a studio system, a replacement part. Here you see the parts. So here's the printed part. Here's the original. First of all, the printed part is lighter just by having the virtue of having the flexibility to print an honeycomb infill pattern inside the part. Most of the load is on the outside, so you don't need all of the material to be present inside. And so you can control just how much of a honeycomb there is, the density of that infill. And so there's a 17% mass reduction. This is, of course, faster. It takes a week versus 2 or more weeks. It's a cheaper part. It's a lower cost part to produce. You don't have the waste of CNC machining. And the next step that they're taking is they're going to explore topology of optimization. So this is the first cut at it. They'll test it, evaluate it, do some simulation, then print it. And so then the idea is the part can be even faster to print. It could be a lighter part and actually stronger. Another example, and the reason I like this example is you would never buy a metal 3D printing system so that you could print relatively, I'm going to say relatively simple and small parts on your manufacturing floor. This is not a super complex part to machine. It would probably take, I don't know if it's 1 hour or a couple hours. It's not a giant job, but this is the beauty. If you have the metal 3D printer, just design it in CAD, throw it in, and then you'll have the parts. So this is a spring holder. This connects a spring to another part that moves around. I'm gonna see if I can play the video. Hopefully it's not too loud. So you see this is right in here. The action is right in the part that rotates the part around. This is the sheet metal is going to rotate in a minute. It's mesmerizing, isn't it? All right, I think you get the idea. So this is a part that's part of this assembly. Let's see, there it is, rotated. So, all right, so let's, whoops. So why print it? Well, the part wore out, the part broke. So here's the original part. Here's the design part that reverse engineered, but also improved the strength of it. Here's the part in fabricate. You see it's a very light part. It's about 8 centimeters. So that's just about this long. Here are the printed parts. And this is a part that is going to see a few thousand cycles of loading every day. So this is a great fatigue application. So the impact is ability to print replacement parts relatively quickly for the manufacturing floor, no CNC machining, lower lead times, lower costs, and make better manufacturing tooling, manufacturing parts. These parts are not only way less, but they're stronger. And of course, you can do this kind of optimization because you have the design freedom that you might not have with other manufacturing or other fabrication processes for these manufacturing tool. Another great example, so this is from Greece. Greece, Bazigos is the largest mold maker in Greece. And it's working towards really becoming a leading tool maker in all of Europe. There's a lot of equipment, a lot of complex advanced equipment, and they've recently brought in a desktop metal studio for the application being mold inserts. So I'm going to show you one example of these mold inserts. So basically the part that's getting molded is this cable gland and made out of plastic. Here is the profile that's used for it. I don't know if you can see this, but this is a relatively precise, relatively small part. Here it is, maybe in a close-up. And the whole point is, with a studio system, you print this in H13 using the fine resolution print head and start using the part with only just a little bit of, for the critical dimensions, a little bit of post-processing. So you have basically a new level of flexibility in creating mold inserts. You don't need to machine the tool steels from a large block of steel. Next example is Ultra Machining Corporation in Monticello, Minnesota. I was there a few months ago. It's a great place. It's a family-owned business. The interesting thing about their manufacturing floor is there's more machines than people. This is a company that has invested a tremendous amount of capital and effort in robotics. And so what you have is these centers where you have 3 or 4, I'm going to show you, these cells where you have 3 or 4 operation and really a robotic arm moving a component from one step to the next. And so it's great to use all this automation, but it means every time you have a new part that you need to pick up, the end effector that picks up that part, the profile of it needs to change. And you see, so that means for every new part, you might need to make several of a new type of end effector. So here you have the design. And these end effectors, it turns out, even though the parts aren't very big, they're just a few inches long, because of the precision required, they easily take just one pair over a day of machining time. So instead, they're now 3D printing the near net shape of the end effector, and just a couple of the key dimensions are machined. And so what you have is, for these multiple grippers that you sometimes need to A, replace, and B, add to the line as you add new components, they're featuring new complex geometry. The CNC is a bottleneck, and so 3D printing eliminates that bottleneck. So in this particular example, you have, instead of needing over 12 hours to machine a pair, you just need an hour and a half of some post-processing. And by the way, that hour and a half can be on a simple Bridgeport instead of a CNC machine you got to program. And so it's probably a different operator, definitely a different machine, and a lot less time. You can remove over 90% of the effort required. The last thing I'd say is, or point out, is the printer, you can print multiple parts, and the debinder and furnace are designed for batch processing. So you print for a whole week and print a full, 30, 40, 50 of these parts. And then in one debind and one sinter run, you can sinter all of these parts and get them. All right. So that's a bunch of examples from the manufacturing floor. Now let's talk just a little bit about mass production, because it is also on the manufacturing floor. So binder jetting for mass production. We have learned, developed processes to use the same MIM-like powders for both the studio systems, bound metal deposition, BMD process, and binder jetting. Binder jetting, of course, it's a process similar to how you're printing with your inkjet printer. It's just that what gets printed layer by layer is a binder that selectively defines where the metal powder particles will become solid and where they won't. And so both processes use a metal powder, an organic binder, and in the furnace, the metal parts are sintered with a binder totally removed. What are the wins? Why go to binder jetting on the manufacturing floor? Well, first of all, the giant win is you eliminate tooling. You no longer need to have molds or work holding fixtures if you're CNCing parts. You can just print without the constraints and the lead times of tooling. You can reduce tool wear. If you can print with binder jetting, you can print, of course, hard to machine materials such as tool steels, but also other materials. It's really a fixed labor cost. It's like you load the dishwasher. I don't know if this is going to work. You load the dishwasher, and then the dishwasher washes all the dishes for you instead of washing each dish by hand. I used to wash dishes in a restaurant. So you reduce the individual labor cost per the part. There's a lot less setup cost. You can now make smaller jobs more economical. Because you don't need to create tooling for a relatively small 1,000-part run. And you do reduce the manufacturing steps. There's a lot of parts that might require 20 manufacturing steps, and now you 3D print the near net shape, and now you reduce it to 4 or 5 steps. We see that all the time. And the other piece, so you reduce the costs of parts you're producing. The other benefit, though, is you can increase revenue by producing parts you couldn't before. We've seen a lot of examples where companies are machining 3 components, welding them together. Instead, you can do assembly consolidation, design one part that combines all of those parts and print that relatively complex part. For example, here's a complex part, or here's somewhere we had a rotating manifold. Anyway, you'll see. Oh, here it is. So here's a rotating manifold. So you see, you got this stuff enters, you got the manifold, and you got this part. This would typically be it might be cast or metal injection molded, but then you have to create tooling. If you're going to machine it, this might be machined out of several components. Now you combine them and print parts that you couldn't make before. So the mass production scenarios range from everything from mixed volume production of various geometries, so every part could be different, all the way up to mass production where you're making hundreds or thousands or many thousands of parts per day. Here's just a few examples from the field of the kind of parts. I'm going to hold some of them up so you can kind of see the precision, the size. You can make relatively small parts. Here's a couple gears from a transmission for a power drill. And you can make larger parts. You can make impellers. You can make this. Here's a nice, you see this gear, this wheel, pretty fine features. And of course you can do a nice customization. So this is the shift handles, custom shift handles for cars. All right. Here's real parts being produced by these binder jetting systems. I'll give you just a couple examples to give you a range, because we've talked about 3 different metal systems. So here's a little output pulley for a I think it's a seat belt. Yeah, seat belt, car seat belt. So this is a part just about a few centimeters long. On the studio system, if you're running the studio system all year, you can make a few thousand. If you're running our mid-range shop system, so the shop system with an 8-liter build box, it's probably little bucks like that, you can make almost 150,000 parts per year. And with a production system, the monster, the big boy system, you make a few million. So really, it depends. And you see there's the trade-offs. There's trade-off in terms of what does the system cost and throughput, materials, and the cost per cubic centimeter. The costs go down. So on the one hand, the production system is a more expensive system. On the other hand, you can make parts orders of magnitude larger volume and dramatically reduce price. In other parts, the swivel base, similar part. If you just need 5 or 10 of them, sure, print them on the studio system. And this is a complex part, then you have it without needing any tooling or machining, and they're $11. And so if you want to do some prototype runs, you want to do some design studies, that's great. If you want to produce 100,000 of them per year, then probably the shop system is right. If you need millions, then production system. And last example, so this is a larger part. This part, I happen to not have it here in my metal 3D printing bunker, but this is a part that you can make a few hundred of per year in the studio system, all the way up to almost 500,000 on the production system. And again, the similar, you see the giant decrease in cost per cc or part cost. So again, if you need just a couple, you're doing design, development, maybe it's a replacement part, maybe spending $140 on a part that you would otherwise have to machine and it would cost you probably $300 or $500 is tolerable. If you're going into mass production, you can produce a few tens of thousands with a shop system, or with hundreds of thousands with a production system. So with that, if any of the things you heard today sound relevant, we'd welcome an opportunity to explore with you which system might be right for you. So we invite you to schedule a little one-on-one meeting with one of our 3D printing specialists. So I want to thank you for your time. During that meeting, we can explore, what are you trying to do for the manufacturing floor? Is it end-use parts? Is it manufacturing jigs, fixtures? If there are some parts that might make sense, we can explore getting that part printed. And then getting a bunch of metrics, what is this part, if it's printed, what would that look like ROI-wise relative to how you're producing them today? So that's our invite. I want to thank you for your time. It looks like there's some questions left. And let's see. Are there any questions? Nick, feel free to chime in, that are worth answering for the public.
Talk about surface finish? Both studio, binder jet, all that kind of stuff?
Sure. So surface finish. Well, I'll give you the number and then I'll hold something up to the screen. So the surface finish is the average roughness. So you got a profilometer. We have profilometers. Our customers measure the parts. The X and Y for the studio system are it's exactly 3 to 5 micron average surface roughness, 3 to 5 RA. I don't know if you can, so that's in the X and Y plane, in X and Y plane. In the Z plane, you see the build lines. So for example, this is this part gets built this way. And so there is fine lines here, the build lines that are probably 10 to, I'm sorry, I keep saying probably, it's exact. We measured this 100 times. It's 10 to 15 micron RA surface roughness. So if you run your finger along this edge, you can actually with your nail feel the 10 micron bumps. No, I don't know, you might be able to see that. So the short answer is on the studio, you get 3 to 5 micron surface finish. So for example, here's some sheet metal parts. The top here, the X and Y axis, you'll have 3 to 5 microns, and probably 10 to 15 micron RA in Z. The parts are considerably better, considerably smoother with the binder jetting systems. With the binder jetting systems, it's probably 2 to 4 micron RA. It is rather than FDM, the inkjet nozzle has the ability to put down to 1 picoliter kind of droplet size. So you can really get very precise, both geometry definition and surface finish. So those parts are, I'm not going to say, they're not an order of magnitude better, but they are 2 to 4 micron RA in every axis. So that's that. I see, let's see, one question, average lifespan of the machine. So this is, the lifespan of the machine is, we've been shipping for 3 years and the machines really aren't coming back. So it's my guess is it's some number of years beyond 3 years. There are parts that, depending on how often they're used, after 3 or 4 years may need to be replaced. For example, the insulation in the furnace. We've been printing with some of the same printers for years on our print farm. There's dozens of printers running, not 24/7, but close to that. And so it's the vague answer is it's fairly reliable. It's a number of years. After 3 years, there some parts may need to be replaced depending on usage. And a lot of like when you're seeing cost estimates, they take into account a 3 or 4 year lifetime. So you amortize the cost of the equipment across the parts. So let's see, more question. Difference in material cost. So the material cost is different for the office friendly, the studio system versus binder jetting systems. With a studio system, the material cost, which is the media, it's the rods, the binder mixed with the metal powder. That's $100 to $150 per kilogram. So that's a relatively expensive way to print parts. You're not going to mass produce parts that cost you $150 per kilogram. And so, but if you want prototyping, then the big alternative is machining. And so machining, then all the cost is in labor. So steel might be $5 or $10 per kilogram. But then you have to put in all this labor to create that part. So that's the economics for the studio system. And so that's why this might be $200 in material cost, but you save thousands by reducing labor. With a production system, if you're General Motors, you're not going to buy steel. You've been buying steel for 100 years at just a few dollars per kilogram. So with the production system, we work with powder suppliers. We certify powder suppliers to work with certain binders. We'll sell the binders, and then the vendors, our customers, buy the powder directly from the supplier. Let's see. The cost of the printing system. So the short answer is it depends. It depends on the configuration. It depends on what services are included. It depends on what region of the world. The best bet would be to contact our sales team. We can easily answer that. It's not that it's a secret. It's that the answer varies a little bit. Let's see. Other questions? I'm just gonna jump into this chat. Feel free to keep asking questions in chat. One of the questions is, what's the cost per cc? Because I happen to have those numbers right in front of me, I'm gonna move them. But you see, per cubic centimeter, you have something like several dollars per cubic centimeter with the studio system, a couple dollars or a little bit better than that with a shop system, and then tens of cents, 20, 30, could be 40 cents per cubic centimeter with a production system. So that varies pretty widely. It depends to some extent on a number of factors, like what's the geometry, how hollow is the part, that kind of thing. Okay, back to this. Thanks very much. Will there be slides? Yes, we'll distribute the slides after. What materials are currently available on the shop and production system? Well, currently available, so with the shop system, it's the 17.4 pH steel. Next in line will be the H13, will be tool steels. On the production system is, I mean, there are customers printing steels and as well as precious metals. So production system there's a lot of knobs there to turn, and there's development going on. by us, by our customers. So there's a lot of innovation happening. So multiple materials, multiple alloys are being printed. What kind of finishing process is good for gears? Let's see, for gears. So finishing process for gears. I don't know if you can see. So first of all, what is the surface finish for gears when they come out? Surface finish is exactly what you've heard. It's 3 to 5 micron RA. Now, for some applications, that's perfectly great. Other applications, there needs to be a very precise definition of the gear, either dimensionally or they actually mesh better. And the gears, if depending on the surface finish, a lot of the failure modes are things that happen right between the teeth after they mesh, and imperfections, cracks start to propagate. And so there's a number of processes. One process we and our customers have found works really great is an isotropic super finishing. So imagine the gear being tumbled, but it's being tumbled in a mixture, not just with an abrasive media, but with a chemical. And that chemical reacts with the surface of the gear, just the surface, embrittling it, making it easy for just the surface of material to come off. So now you have this, you have an abrasive media washing away just the top layer. So what you wind up with is, without removing a lot of materials, you wind up with a remarkably smooth finish. And that smooth finish, so here you see it's pretty shiny. I'm gonna show you guys another couple parts. So here's another part printed and then put through this isotropic super finish. You can almost see kind of the mirror-like finish. Here's an engine piston printed with that finish. What you wind up with this isotropic super finishing process is a average roughness of on the order of 100 nanometers. It's orders of magnitude smoother than what you get right out of the furnace. So for some gear applications, for example, let's say it's not rotating a lot, or it's not huge forces, it's not rotating very fast, as printed works perfectly fine. So for example, here's a pretty fine gear, and for this application, it works just fine. For others, if you're turning a lot and reliability is key, then something like a finishing process, this isotropic super finishing from REM Surface Engineering works great. Hopefully I've answered at least part of that. All right, next question. What's the minimum density of the component that can be obtained after printing and sintering? So first of all, when you're printing with a binder jetting system, so the shop system and the production system, the parts are solid. They're dense. They're fully dense parts. And how dense? High 99 and above. It's remarkably dense. As far as the studio system, there is an infill, and I'm going to show you that in a second. So inside, so with the studio, you have the flexibility of defining how thick is the shell, and then what does the infill pattern look like inside. So here is the same part. So you see the same part, but it was stopped printing, not all the way through, so that you could see, well, what does the infill look like? And on this part, you see it is almost fully dense. This is almost as if it was a solid part. This part, it's actually quite sparse. And so you have the ability to vary this infill, and there's trade-offs. There's trade-offs in terms of strength. There's trade-offs in terms of mass, trade-offs in terms of printing speed, debind time. So there's trade-offs. For many engineering applications, when you have some mechanical load, most of the load is actually carried by the shell. Inside, the material doesn't act very much in terms of strength. It's the reason we have I-beams instead of solid blocks of steel, which would be 10 times heavier. And so you can often have this infill pattern, and so the range is probably something on the order of 20% dense, all the way up to 80. So there's a very wide range of adding or removing internal material. All right, so that's the example. If there's no other examples, there's no other questions, we will shut this reluctantly shut this webinar down. And thank you very much for coming. Take a look at our remote learning week. We have a ton of different topics, a lot of different systems, a lot of interesting presentations. Most of the presenters are better than me. The ones that are not know who they are. And so you'll be both educated and maybe entertained. All right. Have an awesome day, everybody. Thanks for stopping by.